Your pointer for you
Oh.
engraved with your name.
Oh, thank you very much.
Take it away.
Thank you. I was asking for a laser pointer before. I had no idea. Thank you. So it's a pleasure to be here. Let me just adjust this. Back at Texas A&M. And I'm going to be telling you about nuclear forces from quantum chromodynamics. And I have to say it's a very exciting time to be talking about this subject because basically we're on the verge of doing it and accomplishing it. And during the next 10 years and likely less, you're going to see some significant progress in this area. And it's really going to result from a community-wide effort of people in the nuclear physics community collaborating with people outside the community, for instance, applied mathematicians and computer scientists. So let's go back to the very beginning here and remind ourselves of things that we know. And I should start off by saying that when I was in high school in New Zealand, I went to Rutherford High School, named after Ernest Rutherford being a famous New Zealander, but I had no idea what that meant. So this is what it means. So at the heart of every atom, there's a nucleus. In the very early days, Rutherford's day, at the beginning, this was just an infinitely massive or very massive charged object. Then as time went by, one understood that the nucleus is actually a composite object. It's not fundamental, it's composite. It's made of neutrons and protons. And then as we moved forward into the 1960s and 1970s, we understood that, in fact, the neutron and proton are not fundamental objects of nature. They're actually composite objects. They're made of quarks and gluons. And the quarks and gluons we believe to be fundamental objects of nature, at least to the length scales at which we know to probe them experimentally. Now, so this looks like a very simple picture, and you see this in your classes and elsewhere. But the interesting thing is, once you understand about the fact that the proton is really a composite object made of massless gluons and very, very light quarks, dominated by quantum fluctuations, then the fact that the nucleus itself really is a composite object really looks like a collection of neutrons and protons, and it doesn't look like a collection of quarks and gluons. That's actually quite remarkable, because the quarks and gluons are basically confined into objects that retain essentially at the 90% level their identity when you put them together. At some point, as you squeeze on a nucleus harder and harder and harder, then eventually it will melt and turn into a fluid. But in the nuclei that we have and that you're made of and this room is made of, a nucleus really looks like a collection of neutrons and protons, primarily interacting through two-body interactions. There are small three-body interactions, but yet there's no statistically significant evidence for there being four-body interactions, but we expect them to be there. So one of the things that happened in the 1970s and been verified experimentally since then is that we know what the underlying theory of the strong interaction is. It's called quantum chromodynamics, which is a gauge theory. The fundamental elements of the gauge theory are the quarks. They carry color indices, red, green, and blue, or 1, 2, and 3, or however you want to label three objects. And they interact with each other via the exchange of gluons, these massless particles. And it turns out that at low energies, one just has four strong interaction parameters: the intrinsic scale of the strong interaction, the mass of the up quark, the mass of the down quark, and the mass of the strange quark, and then along with the electromagnetic interaction. And those five parameters dictate all of low-energy nuclear physics. Right? So we have the theory, we have four strong parameters, and one electromagnetic coupling constant, and that describes everything you see in nuclear physics. That includes, for instance, the spin pairing you see in nuclei, includes the shell structure that you see in nuclei, and also determines the collective excitations you see. Sometimes some particular nuclei behave like they're liquid drops, others like rotors. All of this phenomenology, which is complex and very rich, is entirely determined in terms of a very small number of parameters. So because we know what the theory is, we haven't yet been able to solve it analytically. We know how to solve it numerically, at least important parts of it, and that's what I'm going to be telling you about today. But because you have control of that, and in fact these parameters are input parameters into your calculations, you can actually vary these parameters and ask the question, what happens to nuclei, nuclear reactions, and the structure of matter as you vary these input parameters. So if you, for instance, if you changed the up quark mass by a factor of 10, would you still produce carbon? Would you produce uranium? These are fundamental questions, intellectual questions. So that's on the academic side of things, if you like, and I'm going to say more about that in a little bit. But so from a more practical point of view, you're in a situation, because you know what the theory is and you have these parameters, in principle you can calculate with arbitrary precision low energy processes that you're interested in, such as nuclear reactions, the ground state of nuclei, their excitations, and so forth. We're clearly not there yet, otherwise I'd be giving you a different title and the conclusions would be radically different, but we're on the path to accomplishing that. So just a couple more words about the proton itself. And the community underwent a long-range planning exercise a couple of years ago, and so that led to, of course, very interesting physics discussions. And one of the things that emerged out of that is that we have the ability now to understand how much of the mass of the proton comes from the mass of the quarks, how much comes from the dynamics of their interactions. And the reason that's interesting is because the mass of the proton is about 1 GeV, or 1,000 MeV. Approximately, that's its mass. And if you look at its constituents, it's made of up quarks. The up quark mass is about 2.2 MeV. The down quark mass is about 4.7, and the gluon mass is exactly 0. So you're making this object out of quarks and gluons through their interactions that takes masses of order 2 and 5 MeV and generating an object that's about 1,000 MeV. And all of that arises through the interactions of the quarks and gluons with themselves. So as I mentioned, it's one of the things for us to refine is to understand how much of the proton mass comes from the interactions of gluons and how much comes from the quarks masses themselves. And if you think about this sort of also in the language of some of the modern AMO types of thinking, then the nucleon's an entangled state of indefinite particle number with spin half. So your AMO colleagues impress you by talking about entangled states, and your quantum computing colleagues impress you talking about entangled states. And it really is interesting and important and theoretical challenging. But now think about the proton. It's an entangled state, but of an indefinite particle number. So our universe is an interesting place. I'm not telling you anything that you didn't know. But the nuclear physics is interesting on a global sense because it appears to be finely tuned. So if you think about the production of the elements, in particular the production of carbon, normally how you produce elements is through two-body interactions. You have species A, species B. They come together in a hot plasma and they form species C. And species C interacts with another one, forms species D, and so forth. Carbon's not like that. So in a very hot, in a plasma of alpha particles, then you would expect two alpha particles come together to form beryllium 8, and then another alpha particle would come along and hit the beryllium 8 and form carbon 12. That nearly happens. So what the issue is here is two alpha particles come together to form beryllium 8. Beryllium 8 is actually unstable. It's unbound. So they come together and then they fall apart. So, but if you look at how unbound it is, so the two alpha particles come together, it's unbound by just a very small amount. So it has to live a while to figure out that it actually can't stay together. And while it's in the process of living together to figure out whether it should break up or not, another alpha particle comes along to form carbon 12. And it forms a state at high excitation in carbon 12. And it turns out that in the 1950s, this state was actually predicted in carbon 12 at high excitation, because if it wasn't there, you wouldn't produce enough carbon 12 to be consistent with what we see in our universe, and we wouldn't be here today having this discussion. So nuclear physics is very finely tuned, and further, if you produce carbon and then another alpha particle comes along and turns it into oxygen 16, then you wouldn't have enough carbon either, And it turns out the state in oxygen-16 is there, but it's not in the right place for that reaction to proceed. So one question that you can ask once we develop this technology that I'm telling you about is that you can then vary, for instance, the up quark mass, the down quark mass, and the strange mass, these fundamental parameters of nature, and then ask for what range of parameters do you produce enough carbon, for which range of parameters do you not. So you can really address fundamental questions about our universe with with these numerical techniques that are under development. So this slide came out of a presentation I gave at the KITP. We were talking about the Anthropic Principle, and the discussion I just presented to you was a small part of that. And so if you think about what are the conditions necessary for life, then if you talk to the astrobiologists, it's the existence of a controllable membrane. If you don't have a controllable membrane, then you can't keep all the good stuff inside for replication, and it just falls out, and it's just a big mess. So if you think about the electronic complexity you need to form a membrane, then you certainly can't do it with just the nuclei with 1, 2, 3, 4 nucleons. There's not enough electronic complexity. So you need to go through carbon and you need to go through oxygen in order to accomplish that. And so one of the studies that's underway at the moment is to look at, as a function of the mass of the pion, where can you produce the heavy elements, for instance, carbon-12, oxygen-16, which I'm defining to be heavy for this talk, and which values of the pion mass can you not? And it turns out that where we've been able to do calculations at a pion mass of about 800 MeV, it turns out that it's right on the edge. Basically, they're not finding stable configurations for oxygen-16. So it looks like you would just have a gas of alpha particles and no heavy elements. So at that point, you would conclude that at pion masses that are very heavy, you can't actually produce complex membranes to support life. And so then another question arises then automatically as you reduce the pion mass, where do you reach the ability to actually produce these heavier elements? So switching gears a little bit, if you look at the nuclear physics community, there's a number of efforts underway, and I just mentioned a few of them here, to try and constrain nuclear forces. And in particular, to better constrain 3 neutron forces and 4 neutron forces. And Jeremy here is involved in doing this on the theoretical side of things. And so the community's invested a lot of money, or is in the process of investing money in the experimental community, and one of them is to put together the FRIB facility that is going to focus on looking at the properties of very neutron-rich elements and how they decay. On the theoretical side of things, there's been significant investment now over the last 15 years plus on the theory side, coherent with computer scientists and applied mathematicians, to develop codes and to refine the nuclear forces to take what comes out of experiment, put it in, constrain the nuclear forces, and then develop predictive capabilities for elements and processes beyond what's accessible experimentally. So there's a very tight tie. There will be a very tight tie between the experimental and the theory communities on this matter. And then there's also observation, what this does, for instance, predicting the equation of state on the inside, in the interior of neutron stars and core collapse supernova. You know, one of the things that when I was in graduate school, supernova 1987A went off, and yet even to this day, we still don't know whether it evolved into a neutron star or went through to a black hole. And the limitation of that on the theoretical side is we don't know the nuclear physics well enough. We don't know primarily well enough the interactions between multiple neutrons to determine how stiff this object is as you start cranking down on it. If it's kind of soft, it'll collapse through to a black hole. If it's very stiff equation of state, it'll bounce and go to a neutron star. We don't know that well enough yet. This will be understood in the next few years. And of course, one of the famous observations that you're all well aware of is the observation of gravitational waves. So you had the spin down of 2 black holes and the coalescence of 2 black holes. And if you look at the theoretical predictions here, what's shown is the frequency of the gravity waves coming out of 2 black holes merging. You find that, in fact, there's a part of the spectrum at high frequencies, if you compare this region and this region, that are different, and that difference is entirely due to what the nuclear equation of state is. Okay, so depending on how soft or how stiff the nuclear equation of state is, it affects the spectrum of gravitational waves emitted by these astronomical, no pun intended, events. There's another set of experiments that are underway in nuclear physics and also in high energy physics, looking at fundamental symmetries on the high energy side, looking at neutrinos and so forth on the nuclear physics side, also looking at neutrinos, electric dipole moments, and also looking for violation of fundamental symmetries in the form of double beta decay experiments. These are all part of the future of our field as we go forward. From a theoretical point of view, as somebody engaged in numerical calculations and also from effective field theory calculations, then if you look at the interactions of, say, fundamental particles that we either know about, such as neutrinos, or ones that we'd like to know about, for instance, candidate dark matter particles, then generally, as I mentioned, a nucleus is looks like a collection of nucleons to a large degree. So one can then imagine scattering a neutrino or a dark matter candidate from a proton or a neutron inside a nucleus, and that gives you the first rough estimate of how strong that interaction is going to be. And then that gets used to set limits either on the existence of dark matter or on the properties of neutrinos. But also from strong interactions, the nucleons interact with each other, and they can also interact with each other while they're actually interacting with the external probe. And so here you have two-body interactions that modify what this probe sees. So this is a form of interaction which tells you that the nucleus is not just a collection of neutrons and protons, it's a collection of interacting neutrons and protons and other stuff. Okay, so these are quite difficult to get at experimentally. They're typically at the 5% level in a calculation or in a cross-section, but they make a difference, and they can make a difference between discovery and not discovery, and they can, I'll say more later on. And there's a hierarchy, and so, for instance, there's also, you can have three nucleons interacting at a point together when they interact with the external probe, and that's also a contribution. So far, there's no evidence for this type of structure, but precision nuclear physics experiments are bound to uncover these things at some level. They're expected to be sub-%, but they will be there. And then another thrust in the nuclear physics community going forward is to look at what is the gluonic structure of a nucleus. So I mentioned earlier on and stressed the role the gluons play in neutrons and protons. Nucleus is a collection of neutrons and protons, and so it's a collection of gluons and quarks. Now we understand well from lots of enormous amounts of effort to study the quark structure of nuclei, and we're still making discoveries there even today. But getting at gluons, because they're electrically neutral, is very difficult. They're also electroweak neutral. So one has to really stand on your head, and the experimentalists have to be remarkably clever in order to really look at what are the gluons doing inside a nucleus. And so part of the long-range plan that we have in our community is to build an electron-ion collider. So this machine, which is sort of the outgrowth of the heavy ion program and the electron program at Jefferson Lab, this is sort of the natural outgrowth of those two programs to study with electron collisions on nuclei what are the gluon distributions inside a nucleus. And you're going to see things from the gluonic interactions that you know in the quark interactions. There's going to be something like the EMC, for those of you who know what that is, involving gluons. That's never been seen before, really, and so that's something that an electron-ion collider, or one of the many things an electron-ion collider can probe. Okay, so on the program of acquiring and calculating nuclear forces from lattice QCD, this is a roadmap of how it is envisaged this will proceed, and this is the path that we're slowly following. So the first thing is you solve QCD. Okay, it's a very short sentence to say, but we've been working on it for decades and it's still not done yet. The computational power and the algorithm development that is expected to occur during the next 3, 5, 10 years will actually allow us to do this. So we're going to be entering the exascale of computational power, which is orders of magnitude above where we are today. And our estimates for how much computational power is going to be required to perform these calculations fits right into that window. So one can take a couple of paths once you can solve QCD. One is you can calculate things directly. For instance, what is the spin content of the nucleon? And you can compare directly with what comes out of experiments, for instance, at JLab and Brookhaven. One can also then try and extract the nuclear force. So a nice thing that happened starting in the 1990s was an organization of the nuclear forces in terms of small expansion parameters. This was initiated by Weinberg. The community's been working on this for a while, and Jeremy's involved in this. And we're now at a place where we've gone to several orders in the small expansion parameter nuclear forces, and we can use this to calculate and develop predictive capabilities and understand what's included and what's not included. So one objective is going to be to determine these nuclear forces to some level of precision with these very large-scale numerical calculations. And once you have the nuclear forces, 2-body, 3-body, 4-body, and also their interactions with external probes, then one can take that and go in through the periodic table and extend greatly the range of lattice QCD calculations. I expect in the next 10 years we can get to carbon at some level from lattice QCD. We're certainly not going to get to calcium or beyond, but by constraining and determining these chiral nuclear forces, we'll be able to get significantly through the periodic table. So let me just make some comments. So I have a couple of slides here just to draw analogies with QCD. So if you think about how QED and electromagnetism was constructed, then there was a large number of experiments on electrostatics, magnetostatics, what happens when you run currents through wires, what happens when you put these charges here and you put a conductor there. Then there was some thinking that went on over an extended period of time. And then perhaps a great prediction of this was, of course, the existence of electromagnetic traveling waves where you could take energy from over here and move energy over here just through the photon field, not involving electrons and so forth. So then experiments were performed, and then, of course, it was verified, and then we have cell phones and lasers, and people are now free to do whatever they want with the electromagnetic interaction and make web pages and so forth. A similar type of path was taken. Oh, what happened there? Sorry. A similar type of path was taken for quantum chromodynamics. For the strong theory, there's experiments. There's lots of experiments, lots of detailed experiments. There was some thinking that went on, and then equations were written down that you could actually write on a coffee cup. I stole this image from the CERN theory webpage. It's very nice. And there's direct analogies between electromagnetism and what you find in quantum chromodynamics. Electromagnetic waves, these travel over great distances from the cell phone tower to your cell phone. In strong interactions, you don't have these long traveling waves. They're confined, but you do have excitations of the gluon itself. So there's a large experimental program underway to look for these excitations and to map them out. And that's moving along with the GluX experiment in particular coming up and underway. Electric charges, you have color charges, and if you want to take a quark and an antiquark and pull them apart by 1 Fermi, which is 10 to the minus 15 meters, it requires a force of 200,000 newtons, which is big. And perhaps there's two things that really define QCD and differentiate it from QED, is it's intrinsically nonlinear. Photons pass through each other, gluons do not. And it's essentially quantum mechanical. So if Planck's constant was 0, then the proton would weigh about 10 MeV. And it's the fact that Planck's constant is not equal to 0 is why the proton weighs about 1 GeV, or 1,000 times that, compared to 10 MeV. So it's nonlinear, it's intrinsically quantum, and both of those features are what make it very difficult to explore analytically and what forces one to use large-scale computation. So what is lattice QCD? So lattice QCD is actually quite simple. It's you would ideally solve quantum chromodynamics in the continuum and infinite volume, and in Minkowski space, you can't do any of those. What you can do is you can solve a discretized version of QCD on a grid in a finite volume and in Euclidean space. And there's various reasons for those things that I won't go into. The first two are obviously just because of the finite size of a memory of a computer, and the other one is a little more subtle. Excuse me. And so you discretize space-time onto a grid. You have a four-dimensional grid. It's very big. Typical today, you can look at 64 cubed by 192, 100 to the fourth, or something of that size. And you take various bits of the grid, the space-time, and you push it out to different nodes in your computer. And so one's run these types of calculations on more than 1 million cores. Running on 32,000 cores is standard. Running on 8,000 GPUs is not outrageous, and so forth. So that's the typical scale of things. And as long as the lattice spacing that you choose, the discretization of your space-time, is small compared to the typical length scales that you're interested in, then the result is very, very close. And you know from formal relations how to systematically remove and take the continuum limit as A goes to 0. Similarly, if the volume is big enough and it contains the system you're interested in, you can do your calculation there. It's slightly wrong, but then you know formally how to systematically remove how wrong it is and recover the infinite volume limit. And at the end of the day, it's all about evaluating a path integral. So you want to ask what is the probability amplitude for a particular process by integrating over all the possible quantum fields at each point in space-time. That's what this means. And at the end of the day, this turns into a statistical averaging process. So you calculate a whole sequence of snapshots of the vacuum, and then you evaluate the quantity that you're interested in those snapshots of the vacuum, and then you average them. That's all lattice QCD is. But you need a lot of people and a lot of computational effort to do this. So there's a national collaboration called USQCD. This is about 120 people or so. It's a well-organized collaboration. There's a scientific advisory committee, scientific program committee, an executive committee, a software committee, and it works coherently to advance the goals in both high-energy physics, lattice QCD, and nuclear physics, lattice QCD. And so this is a photo from a couple of years ago. In fact, we're back at JLab next week for the 2017 all-hands meeting. And some ancient history is that members of the USQCD collaboration, particularly Columbia, Norman Christ's group, designed and fabricated the QCD-SP chip and the QCD-OC chip. They won the 98 Gordon Bell Prize, and that chip design is what led IBM to build the Blue Gene series, the Blue Gene L, Blue Gene P, and Blue Gene Qs. They're all direct descendants of the QCD-SP. They're really lattice QCD machines. By far, these are the best machines for performing lattice QCD calculations. They just scale linearly off to infinity, where infinity is how many nodes there are. So what you're doing is you're really finding a convergence of two Nobel Prizes here. So the Nobel Prize for the electroweak interaction, you have the quark masses. That's something given to you by the Yukawa couplings of the Standard Model. And then you have the Nobel Prize for asymptotic freedom, and that tells you that you have some coupling constant in QCD, and as you probe it with lower and lower energies or longer and longer wavelengths, the coupling constant actually becomes larger and larger due to quantum fluctuations, to the point where it becomes so large that chiral symmetry is broken, and in fact quarks and gluons are not the relevant degrees of freedom, but protons and neutrons and nuclei are. So this is a picture of nothing. This is a picture, a snapshot at one instant in time of the strong vacuum. This is what the gluon fields look like. And what you see is that for QCD, you have non-trivial topology in your gauge fields. So the gauge fields can wind themselves up in color space and space space, and you have these knots called instantons. These are objects of maxima, extrema in the action density, and also local maxima in winding number, for instance, these GG dual, for instance. And so this is what a snapshot looks like. This is about 4 Fermis, or 4 times 10 to the minus 15 meters. This is a cubic slice. And these are these extrema in changes in topology and action density. And if you ask how does a quark move from one point in space-time to another point in space-time, there's a probability amplitude. So for instance, this is a picture of what a quark propagator looks like. You create a quark here, for instance, and you ask, what's the probability amplitude for finding it somewhere else at some later time? and this is what it looks like. It's not what you see in textbooks. It's not a nice smooth function because it gets buffeted around strongly by what these fluctuations in topology and action density in the strong vacuum do. So that's why you see these bumps and maxima and minima in here. It's getting buffeted around by these things. And then if you ask what does a pion do? So this is a picture of what a pion does. It was created at some time. At some time T0 is created at this white cross, and then at some later time, this is where you could find the pion in this volume. So you see that it's strongly influenced by these extrema in the action density, and this one wants to be over here. It's sort of fallen into this hole generated by an instanton, an extrema in the action density sitting right here. How much computing? So it's kind of hard to grasp the magnitude of the computing required to do these calculations. So the desktop machine, this is taking you back to 1994 maybe. I forgot to do that. So hopefully they won't call back. Sorry. This is taking you back a long time, but this performed about one gigaflop. And so if you ran this for a year, you'd get about 9,000 core hours out of this. So this is running a calculation continually for a whole year. You get effectively 9,000 core hours, 8,700. And so we're going to be deploying exascale machines by around about 2022, 2020, somewhere in that interval. Hopefully exascale machines become available. So that's about 1,000 petaflops. So one exaflop machine is about running 1,000 petaflop machines all together and coherently. That's about running 1 million teraflop machines together all coherently. And that's the same as running about 1 billion of these objects coherently, all connected together with very fast interconnect. So that's the magnitude of the computing power that's going to be deployed in the next few years, is about effectively 1 billion of these types of objects. So the Chinese are kind of skinning the US at this point. They put out the fastest machine, and they've got 3 of the top 5 machines now. 125 petaflops. It consumes about 20 megawatts. It's got 11 million compute cores and about 1.3 petabytes of RAM. So that's quite a machine. And the goal here is for the US to deploy 100 petaflop machines late this year, early next year. That's currently the schedule, and exascale machines around about 2022. So if you look at what's been accomplished in hadron masses, then of course, if you want to do nuclei, you can't do nuclei before you've done the basic things. What is the mass of the proton? What is the mass of the pion? You got to get the basic stuff right. So I said there's 4. So this doesn't include quantum electrodynamics, so alpha 0, but you've still got 4 parameters you need to tune here. You've got the scale of the strong interaction, you have the up mass, the down mass, and the strange mass. So you need to pick 4 objects that you know well from the particle data book to tune up your parameters in your calculation, and then once those are tuned, you can make predictions for everything else. Okay, so that's what's done here. The open circles correspond to an input parameter, an input constraint, for instance, the kaon and the pion. And in some calculations, the cascade's been used to set the scale. In other calculations, the omega's been used to set the scale. And then everything else, all the solid points, correspond to predictions. And the horizontal lines correspond to what's in the particle data book. So you see that once you've actually tuned up the input parameters to these numerical calculations, you make predictions, and those predictions agree with the experiment in every case. Sometimes the error bars are bigger, sometimes the error bars are smaller, but in every case you have recovered the correct quantity in the particle data book for masses. So I'm part of a collaboration called MPO-QCD. We've been together since about 2004. Some people have come in, some people have come out. And the objective is to calculate light nuclei and nuclear forces directly from QCD. And you see we have a range of people here, from graduate students all the way through to near retirees. So this slide sort of captures what I said before. One's going to start with these calculations of hadrons in the strong vacuum. One is going to then perform calculations, analogous calculations, and extract and refine and constrain the nuclear forces, which are now ordered. So there's a now well-defined ordering in these nuclear forces. And then you're going to take these forces and make predictions that are reliable up to the precision of the calculation that you know a priori what it's supposed to be. So you're actually going to have predictive capabilities, and you can completely quantify the uncertainties associated with those calculations in regions where you don't have experiment. Okay, so the big difference here is you can actually predict in regions that you can't verify, and you know that you can trust that result with a given uncertainty. So that's a big change for the field. It's not supposed to replace experiment. Of course, it's never going to. It's supposed to complement. So, for instance, the experiments at EFRIB to refine the 3-neutron, 4-neutron forces, those are going to be complementary. Those will be done with lattice QCD, and there's a decomposition and a checking and a verification that's going to enable. So we've been doing calculations at unphysical quark masses simply because calculations of the physical quark masses require a lot of computational time that's not available today. There's a calculation at a pion mass of 800 MeV. So this is quite a heavy pion, and the nucleon in this case is about 1600 MeV. And you see that we've been able to calculate all the way through to 4-body systems quite cleanly. So, for instance, the deuteron is bound at this heavy quark mass. The neutron-neutron system is also bound. The helium-4 is bound. There's a 0+ state, the ground state, and helium-3, the half-plus state, is also sitting here, quite well resolved. It doesn't actually cost much more computational-wise. Once you can do light nuclei, you can do light hypernuclei too. So here we have nuclei containing one strange quark. Is lambda in it, is the hypertriton with a 3 half-plus ground state, and here again with two strange quarks, 2 states, and in cascade. So the technology is sort of now in place where we can get the low-lying states of light nuclei once you have the computational resources to be able to calculate the number of quark propagators that you need. And this was done about three and a half years ago, and since that time we've been working at both lighter quark masses and also to look at the properties of the nuclei, like axial charges, magnetic moments, inelastic nuclear reactions, and so forth. There's a group in Japan that's also been using similar methods to perform calculations. They're able to get much more computer time because the Japanese have the K machine, and that was a dedicated project on that machine, so they've been able to work at lighter quark masses than in the United States. So here's our result for helium-3 binding at 80 MeV. Here's our result at 450 MeV, and here's two results from the Japanese collaboration. It's a mess. The error bars are big. They certainly need to be, these calculations need to be repeated with much higher statistics, new algorithms and so forth to reduce these error bars. But nonetheless, you see a pattern, right? Things seem to be getting lighter. This is experiment as you reduce the quark masses. This is what you see for the deuteron. The deuteron at 800 MeV is bound by about 25 MeV. It's about 15 MeV as you come lighter, and experiments about 2.2 MeV. So it's on the path. As things get lighter, it becomes more challenging. So, and also you see as you increase the number of nucleons, you see these error bars blow up dramatically. It becomes more computationally demanding. We think we've come up with a new way to deal with this that will make life easier. So taking these results, a group of nuclear many-body theorists centered out of Italy in Trento took these results and basically realized the dream. So what they were able to do is they would calculate the 2-body systems. They took the lattice QCD results, calculated the deuteron, the dineutron, and helium-3. So this is the result of the lattice calculation. They then tuned the nuclear forces in this effective field theory to reproduce the 2-nucleon and the 3-nucleon system. They then predicted the 4-body system, which is here. This is the lattice QCD result. This is the prediction from the many-body calculation with these constrained nuclear forces. And they agree with an error bars. And then they could predict 5-body system. So this is lithium-6, this is helium-5, lithium-5. So this is kind of the first realization, the first steps towards realizing the dream at the beginning. You perform lattice QCD calculations, finite restricted number of systems. You then constrain the nuclear forces and use those nuclear forces to predict far beyond where you could do the lattice calculation. And that's exactly what happened here. These error bars are big. These red error bars are big. It's not their fault. It's our fault because our uncertainties in the lattice QCD calculation are big. If we can shrink those, which is the plan, then these error bars and these predictions will be smaller. So this is at an unphysical Pine mass. This is in an unphysical world. But this is exactly what's going to happen when you get down to the physical point. You're going to do these lattice calculations. You're going to constrain the forces in the effective theory, and then you're going to make predictions beyond where you can do the lattice calculation. Let me skip this. So lattice calculations allow you to do crazy things because you're not constrained by reality. And kind of everybody's dream, really. So what happens when you put a neutron in a magnetic field that's enormous? Okay, so you can do that, and we did it. So here's a neutron. This is again an 800 MeV pion neutron in a magnetic field. So this is about 10 to the 20 Gauss. So the biggest magnetic fields that are known in the universe sit around about here from magnetars. But that's not going to constrain us because on the computer we can make them huge. So we get a 10 to the 20 Gauss magnetic field. So the neutron loses about 400 MeV in mass. It just gets stripped off. And the reason for that is because the quarks are basically forced into Landau orbits and they get tighter and tighter and tighter as you crank up the magnetic field. The object becomes more compact, and so the interactions with gluons become less and less and less, and eventually it'll just become a 10 MeV mass proton eventually. So the interesting thing here is the spin down of the neutron basically is a straight line all the way from 10 to the 20 Gauss. Quite odd, because before we did this calculation, I was asking people, what happens to the neutron and proton when you put it in a magnetic field? What does that mean there? And so every possible curve you could imagine drawing was an answer I got to this question. And mine fell somewhere in the middle. But it turns out that the spin down neutron just goes straight down, linearly. Now, the spin up is different. It does all sorts of things. And really what's going on here, this looks like an avoided level crossing. And this is the point out here. Because you have a whole lot of other states in the tower that are all coming down like this. And so you will see just a whole pile of avoided level crossings. And so the spin up state is really doing this. There's no way to predict what this is going to look like. This one I didn't predict either, but this one I can understand. This one, no. So it's kind of neat. But you can also then ask, what is the magnetic moment of a nucleus? So just in the same way as you can do the neutron, you can put the nucleus into a magnetic field and ask, what does it do? Well, so this is kind of curious. So the red dashed lines correspond to what's measured experimentally. So this is an experiment at the physical quark masses, pion mass of 140 MeV. And the blue bands are the results of the lattice calculation at a pion mass of 800 MeV. Okay. So within, these are very close. They're not exact, of course, but the pion mass has varied enormously over this range. And it turns out the magnetic moments of nuclei just are pretty insensitive to the actual values of the quark masses. And it turns out that extends to the hyperons and the other baryons also. It's pretty much insensitive, but the trick here is to define the units. So this is in units of the magnetons defined by the nucleon mass at the value of the pion mass. So for the red lines, the nucleon mass is 939 MeV. For the blue lines, it's 1600 MeV. But once you take that out, then pretty much what you're finding is completely insensitive to the quark mass. Another thing we're able to do with this is measure the calculation of the first inelastic nuclear reaction, in P to D gamma. So this is a very simple process. Just have a low energy neutron, comes in the vicinity of proton and it captures. It's the first process in the Big Bang to produce elements. And so at the quark gluon level, there's a diagram that looks like this. So I made this diagram 20 years ago and basically made the comment that you can never do this with QCD. You have to use effective field theory. So much for what I knew. So now you do this with lattice QCD, and the heart of the matter is to establish these correlated two nucleon interactions with the magnetic field. You can calculate this, and then as a function of pion mass, you find these points. You have an extrapolation that gives you some region here, and you ask at the end of the day, what is your prediction for this reaction cross-section from lattice QCD? It's about 334.9 plus or minus 5 millibarns at this incident neutron velocity. An experiment is 334.2 plus or minus 0.5. So the central values being so close is an accident, right? Because the lattice calculation is plus or minus 5. But nonetheless, these are the same. These are consistent statistically with each other. And if you didn't have these correlated interactions with the electromagnetic field, the prediction would be 306 millibarns, which is way off. So there's another interesting feature, and I'm just going to go through a couple of things. Because these lattice calculations have pointed to a number of things. The magnetic moments are just one example. This is another. That the lattice calculations are actually revealing aspects of the strong interaction that tell us that there's underlying structure there that we don't quite know what it is yet. And it's something that you can't access experimentally because it depends on varying the pion mass and varying the quark masses. So there's some structure being revealed. So at first what was thought to be obviously impossible, here's a plot of the axial coupling in the nucleon, Ga, as a function of the pion mass over a large range. So this is a big number. This is about a GeV roughly of order. And you find that this axial coupling constant is essentially independent of the quark mass, and it takes a slight upturn as you go towards the actual physical value. But over a large range of quark masses, this is basically constant. That's what you see with the magnetic moments. You see things that are varying very slightly with the quark masses. And if you'd asked before these lattice calculations happening, what does GA do? Well, GA was going to do this. Right? It certainly was not going to do this. It was going to take off. So there's structure there. Could be a spin flavor from large NC. It could be the non-relativistic quark model. Don't know yet. Maybe somebody in the room can answer that question, but there's certainly a fundamental question there to answer. So something else we looked at recently, and I'm not going to dwell on this too much because of time, we're able to calculate, for instance, the axial matrix element of the in the triton and the Gamow-Teller matrix element, and we came up with a number. We're also able to calculate the cross-section for a proton-proton fusion. That's something that's of great interest because it has to be theoretically calculated. One can't get it experimentally just because of the Coulomb barrier. And lattice QCD, we were able to actually perform that calculation. It was quite straightforward. And effectively, again, it comes down to identifying these correlated multi-nucleon forces, in particular this one. So we're able to calculate this one, but we're also able to calculate this one with enough precision to be able to predict PP fusion and the rate. So people can ask me about that later on, but I want to say a couple of things about some work that we've done in the last few months that's directly relevant. So when you do these calculations, you're doing a statistical averaging. As I mentioned before, you take snapshots of the vacuum, you calculate what you're interested in, you take the average value, and that's the result of your lattice QCD calculation. However, there's a lot of information about what is the distribution of those things that you're actually pulling out. So I do this averaging, but there's moments, there's skewness, variance. What is the actual distribution that you're pulling out? So it turns out that in fact, there's an enormous amount of information that had been previously thrown away. If you look at what, in particular, the phase of your correlation function is doing, so your correlation function is a complex number, there's some number out the front, there's a real part and an imaginary part, looks like an averaging of the particular snapshots, then in fact you find it has remarkable similarity, it's in fact well described by a stable distribution. And in fact, the phase is the thing responsible for the bad behavior of the signals. And the phase undergoes basically levy flights. As a function of time, you see the phase sit in one location, and then it'll take a big hop over somewhere else, and then sit around here, and then it'll take another jump. So these are things, this is behavior you see in the stock market. It's what you see in the distribution of cancer cells in the body. You see these stable distributions, and you see it also in lattice QCD calculations. This is a stable distribution for a phase subject to periodic boundary conditions, 0 and 2 pi. And what's really going on here is that these flights are the things that give rise to the degradation of the signal or the decoherence into hadrons. And it's what costs enormous amount of computer time because at late times this gets out of control with finite sampling. And it turns out that what you can do is you can greatly improve your calculational ability by truncating in time how much of the signal you actually want to look at. And so we're putting out a paper tomorrow, one hopes, and there's a paper came out a few weeks ago looking at this. So this is a typical signal you see, for instance, for the rho mass with a finite number of calculations. So typically in this region, you can pull out what the rho mass is, and all of this stuff is just junk. It's thrown away. This is called the signal-to-noise problem. The signal degrades exponentially relative to the noise in this region, and generally it's just discarded as waste. To improve this with traditional methods, you need an exponentially large amount of compute time. It turns out that this signal-to-noise problem is, in fact, a sign problem. It's a sign problem in estimating that phase. And by truncating, doing some nice phase reweightings, then, in fact, you can turn this signal into this signal. So you recover error bars that are not degrading exponentially, but the answer that you get is wrong. But it turns out that this bias, you know what this bias is, and you can actually extrapolate it away. So what's shown here is the gray line corresponds to what you get out of this region from about 1 million measurements. And these blue points correspond to what you get doing this new trick. And then this is the extrapolation with about 100,000 points. So it turns out that in this region, which was completely garbage before, you can actually you can get precision measurements and recover what you wanted. You can recover the signal. So this effectively is a way this fixes the sign problem to some level. You turn the sign problem from an exponential problem into basically a parallel problem. And why this is important is because when you're dealing with nuclei like the alpha particle or 5 particles, this flat region, this approximately flat region, just doesn't exist. The correlation functions go straight into this region. So now we're in a position to analyze these regions and actually able to make predictions for the even heavier nuclei. So combined with new compute resources, I think things are looking good. So I just got a couple of minutes left, so let me make some final words here. So what is the state of the art in the field? This is about 2 years old now, but it's sort of pretty much the state of the art. You can include fully dynamical electromagnetism. You can fit the up quark mass, the down quark mass, the strange quark mass. And then you can predict things, for instance, the neutron-proton mass difference. And the red point corresponds to the neutron-proton mass difference from a lattice QCD calculation, and the horizontal line is what you know from experiment. And they agree. So you can actually do now precision things that are of critical importance for nuclear physics, isospin breaking, charge symmetry breaking, and so forth, and you can get the right answer. And these correspond to a whole set of other observables. Where you see this blue band, it means that the lattice QCD prediction is more precise than experiment, and represents a challenge to experimentalists to prove it wrong. So let me make some comments. So during the last year and a half, the community came together to estimate what computational resources are needed for nuclear physics for the next decade. A report was put together, and the word draft within the last couple of weeks has been removed from this report. It's now been accepted. It's 380 pages, and it basically outlines what's needed to accomplish the science mission of nuclear physics, what computational resources are needed. It covers everything, theory, experiment, the whole lot. And so one of the interesting things here is a compilation. This is sort of a rough summary chart of what's needed. So this is conventional core hours in billions of hours. So experiment needs of order 10 billion conventional core hours. And then some of the theorists need of order 30 billion accelerated node hours. So, for instance, this might need, this is 30 billion GPU hours or something to accomplish the goal. So that's the scale of the computational resources needed. But we've now identified the need. We've identified what you have to do this, and it's a case of now just executing this. And we hope this plan will be helpful. And as I mentioned before, it requires a large-scale coordination. So here's basically the map of one of the collaborations, and this is the USQCD map, the nuclear physics one, of who's collaborating with who, what institutions are involved, applied mathematicians, computer scientists. We have people from NVIDIA and Intel. There's NDAs with these people, computer scientists, and so forth. It's a complex community of people that are required to do this, because there's so many different skills needed to take the physics problem, map it to something that can run fast on a big computer, make it run fast on a big computer, and then analyze it and get the physics. So this is not something one person can do. This is a community-wide effort, and I think that we know what we're doing here. So let me just go to closing remarks. So latest QCD combined with nuclear many-body techniques will provide first principles predictive capabilities for nuclear physics. This is certainly a major change and will be important development for the field. On the road, calculations on physical quark masses are actually revealing unexpected features. And this is going to teach us something at the theoretical and conceptual level that we'll also be able to use. And in fact, that's kind of how this field has evolved, and the field in general has evolved going forward. It's been an interplay between computation, theory, and experiment. All of these things are fed back into each other and to go forward, and this is how the next generation of nuclear physics is actually going to be accomplished. So, thanks very much. Yeah, so that's a great question. So in some sense, it's not a well-defined question, because certainly if I think about what we already know, for instance, about the structure of the nucleon, the nuclear forces and so forth, basically all those features result from chiral symmetry breaking and confinement. Those are the big mechanisms at play there that generate those things. So I think one can study, certainly by inserting probes into the system, what happens as you move things apart, as you inject momentum. And from my point of view, that's going to be sufficient to understand confinement numerically, because I don't see any other information that's going to come out of that except by studying the properties of systems in the same way as you would do it experimentally. So I'm not quite sure. The hope would be analytically you could prove this theory is confining. So far it's only been proved numerically. And I don't see what else one could add to that program to try and say something more definitive as to what confinement is. That's my view. Not entirely satisfactory, but that's where I am. Oh yeah, slide 19. Oh, I've blown it up. Oh, yeah. I've been here before. This one? Yeah, so one of the, as I mentioned a little bit in passing, is that in the 1990s, started by Weinberg, the nuclear forces could be arranged in a with systematic power counting. So that is to say, there's a small expansion parameter identified with the external momentum divided by some scale, and the quark masses divided by some scale. And so that gave you two parameters, if you want to just call them Q or X. And so when you perform calculations, there's a leading order, which is, for instance, Q to the 0, or you can put in the first correction perturbatively, then you can put in two corrections perturbatively and so forth, or even non-perturbatively. And then, but when you perform the calculation, you know that calculation is good up to pieces you're missing, for instance, say, x to the 5th. So you know that you've calculated all contributions out to x to the 4th, and you know what you're missing is x to the 5th. So there's some error bar on your calculation. So that's what leading order next to leading order. So here, for instance, the leading order in the calculation, you just have the contact interactions and pion exchange. And next to leading order, you have new interactions that you have to introduce to get a calculation correct at order x squared and so on. So that's what that means. It's a perturbative diagrammatic calculation. Yeah. No, so it's actually kind of interesting. I mean, you've asked a very broad and important question, and it's one of the slides that I took out, actually. So, for instance, if you want to know what is the spin content of the nucleon. So the issue is how to, so if you took, for instance, the non-relativistic quark model where you have an up quark, and a down quark, that, for instance, gets the magnetic moments very well, right? It gets the axial, has the axial scaling right, but the absolute normalization is a little off. It's something that emerges in the large NC limit of QCD. You get the non-relativistic quark model predictions and so forth. And then when you come to do latest QCD calculations, you recover those sorts of features, right? So then I have a lot of feeling for the non-relativistic quark model in the large NC limit because it looks like they're probably dominating the long wavelength components, if you like, of the proton. So I think that these hadronic models, there's elements, they've captured elements of the picture. I think the non-relativistic quark models captured important elements of QCD. It's not the whole story, but it's captured particular things, and it's done it well. And so I think that it's going to be some combination of all of those things is what emerges, and I think that's kind of what we're starting to see happen. Surprisingly, I thought it was not going to look like that at all, but I think it is. So, complicated question. And this is how you're going to do this. This is how this is going to arise. So there's a couple of ways you can think about doing this. One, you can try and put down sources to look at the long distance behavior of the interactions on the lattice. That's got some limitations associated with it. And as of yet, there's no calculation that shows that the pion is actually dominating the long range part of that force. That's a calculation that will be done down the road, but the precision's not good enough yet. The real way to do that is to, for instance, match onto these effective field theories and perform a whole sequence of calculations. And in fact, working through a range of pion masses is how you're going to do that dissection. Because as you change the quark mass, for instance, this changes, this constant also changes. So there's a lot of evolution that happens. And to really do this dissection of nuclear forces into one pion exchange, contact, two pion, and so forth, you will run your calculations over a large range of pion masses, even lighter than the physical point, to do that dissection. So I think that's on the road to being done. It's not convincing yet from latest QCD. It's on the road to being done, and I think that will be done. That's going to be a central part of the program, in fact.
So there's a Japanese collaboration,
right?
Who actually tried to extract.
They try.
You know if the long distance behavior did that in any way match?
So firstly, they at the physical point, they don't have the statistics, and at heavier quark masses, that long distance behavior does not appear to match. But I think that many of us understand what their problems are. But I suspect that as you get to the physical point, if you go out far enough, there's a chance that you should, by not using nucleons. So you can get at this rigorously by using, for instance, a baryon containing a heavy quark where you can actually define the radius. And there, as you move those apart, then you can look at the fall-off of that interaction. And then you can do that. But that's not been done with high enough precision to say that it's the pion doing it. But at the heavier quark masses, it looks like it probably is. So I think you can do that part, but not with the proton and neutron, with something that you can pin down. Yeah. Yeah.
You talked about various different calculations of masses.
Right.
And these calculations of the various hadronic masses, how do they do for the hadronic
So,
radii?
so the radii are more complicated, but one gets at those through form factors and as a function of momentum transfer. So if you look at the charge radii, the isobictor charge radii, in particular the proton charge radii and axial radii, then these things are all falling into line with what you know experimentally. The electromagnetic ones are statistically in agreement. You need high precision because you want to test this discrepancy. But
We need higher precision right now to know what the right answer is.
yes,
That's a different matter.
yeah, it's going to be a race. Yeah, so these are falling within error bars. These are falling into being consistent with the experiment. So, but it's more complicated than just the mass because if you could pin the hadron down, then you can really ask about correlations here. But for a proton, you don't have that. You just don't have the ability to do that.
If there are extra questions, we talk about them afterwards. Let's thank them again.
Thank you. Very nice touch. Thank you. I like that. Yeah. That's good.
I couldn't say till we experts